So we're going to continue chapter 4. I want you guys to open the SoCal casting model that we started in previous session, where we learned how to use the variables. And please save this model as a new file in the same folder for week 4. And for the name of the model, as you can see on the top of my screen, please keep it as SoCal casting dash, remove the variables, and at the end of the name, put uncertainty in routing. That's what we are going to learn in this model. What do we mean by uncertainty in routing and how we are going to model it? So please do that. Save your previous model as a new file in the folder for week 4 and name it as you can see on the top of my page. And this is what we are going to do in this model. So like the previous model, let me bring this part up. Like the previous model, we have our entities are castings. They go to the receiving dock, then to the mill machine, then to the grinder. And then in previous model, we had the fact that they go from grinder to the finished part store and then leave the system. However, in this model, from grinder, they go to inspection. They go for inspection, and then from inspection, they go to finished part store and then they leave the system. So we add one more location where we perform the inspection operation. Okay, so not a big deal so far. However, at inspection, there are several possible outcomes or outputs that we can have. 12% of the parts that come out of inspection need to go back for some mill rework. 10% of the parts need to go back for some grinder rework. 5% of the parts, as you can see here, will be scrapped. And then 73% of the part will be done. They pass the inspection successfully and they go to the next location, finished part store, and they leave the system. Okay, so that's what I mean with uncertainty in routing, because in previous models that we developed, the routes were certain. You go exactly from one location to another. There was no other choices. But here, that's not the case. When you are done in one location, for example, inspection, you can go to multiple destinations, and each one of them has some probability associated with them. So we don't know exactly for the entity that comes to the system and goes through the process. When the entity gets to the inspection, we don't know exactly where that entity goes to. Depending on the probabilities of this possible destination, the entity may end up in any one of these destinations that it can go to. So that's what I mean by uncertainty in routing. So that's what we want to learn in this model, that how to capture this scenario. The arrival process is still like what we had in previous model. We receive castings in batches of 4 every 60 minutes. Okay, so given the fact that we are going to start by working on the previous model, on the location, I want you guys to please add a location for inspection. And we are going to leave the capacity of inspection as 1. We are able to inspect one entity at a time.
And then we can only inspect one at a time, right?
Yes, the capacity, as you can see, is 1. We can inspect one at a time. Okay, so answer this question. Let's assume the guy in inspection is done inspecting a part, and this part needs some mill rework. And let's assume mill machine is busy processing a part. What happens to that part that needs mill rework? What happens to the inspection and that parts that need mill rework?
Logged.
Because the inspection guy is, because he has to hold to the part that needs mill rework. Just because the mill machine is busy, the guy has to just hold on to the part till the mill machine is idle, and then send the part to the mill machine. So the inspection guy is blocked by mill machine. So he's done with inspecting the part, but he has to just hold on to the part till he can finally send it to the mill machine. So that's what we call as block time for a machine. So what is the solution then? If we want to prevent the blocking of inspection just because the mill machine is busy, what can I do then?
Put it in a pile for rework.
We can create an area that this inspection guy can use. So when the inspection person is done inspecting a part, if the part needs mill rework, or then the guy can just leave the part in that pile, in that bedding area, and then the guy on the mill machine can pick up this part whenever that guy is done. Okay, that way the person at inspection is not going to get blocked just because he has to hold on to the part just because the person at mill machine is busy, right? So that happens for most of the times when we want to model an inspection operation, we do that. So I can create some, I would call virtual location, the locations that you may not explicitly see in the problem statement, but locations that we can put here as virtual locations. So when a part needs mill rework, we can put the part in this pile for mill rework, and then when the mill machine is idle, they will just go pick a part from mill rework and start doing the rework. The same for grinder. But if a part needs grinder rework, I can leave the part in the grinder rework area, waiting area, and then when the grinder is idle, they just pick a part from grinder area and start working on it. And the same for scrap. I can create a virtual area for the scrap, and when the inspection guy is done inspecting a part, he can just leave the part on the scrap area. Okay, so we can do that to take care of this transition. If I don't put these virtual areas, locations here, as I said, what happens is that when the inspection person is done inspecting a part, he has to hold on to the part till he can send it to the mill machine or grinder machine, assuming that mill machine and grinder machines are busy. So the inspection person is blocked, but we don't want that to happen. When the inspection person is done inspecting a part, we want that person to be able to just leave the part in the pile for parts that need mill rework, or in the pile of parts that need grinder rework, or in the in the pile of parts that are scrap, and then start working on another part. And then mill machine and grinder will pick up the parts from the rework areas whenever they are idle, and they can work on a rework. So let's do that then. You can pick any icon. So I'm going to create a location for mill rework, another for grinder rework, and another for scrap. Okay, let's put the labels as well. And for these rework areas, make sure the capacity is infinity, because this is just a pile, right? This is just an area. It can hold as many items that needs rework. So there's no limit on how many items they can hold. So we can just leave the capacity as infinity. And I don't change the rules, the queuing rule to first in, first out. I just leave them as no queuing, as you can see here. I just leave them as no queuing. The reason is that, I assume these are just a pile. So the inspection person just puts the part in the pile, and the mill person just picks any part in the pile. So not necessarily the part that arrived an hour ago. He can pick up any part. And this is just the assumptions I make for this model. Obviously, in your models, in your scenarios, you have to see what rule captures your model precisely. So, and just implement that rule. Here, I just assume there is no queuing rule for these three locations that I added. And I think they're good up to now. Okay. And for entities, we just have one entity for casting like before. For arrivals, our arrivals is like before as well. For castings, arrive to the system from the start of the simulation every 60 minutes for as long as we run the simulation. Now let's go to the processes. So for processes, the casting goes from receiving knock to meal, like before, no problem. We go from meal to grinder, like before, no problem. From grinder to, previously we had finished part store, right? Going from grinder to finished part store. But in this model, we go from grinder to
inspection.
Okay. So in your third line, we go from grinder to inspection. And for the last line, I would say just delete your last line from the previous model. Just for simplicity, just delete the last line from previous model. So right now you have 3 lines, and the last line that you have, we go from grinder to inspection, right? Next, our entity is casting. We are at inspection. But at inspection, what are the destinations that I have? One possible destination is that I can go to meal rework. Okay, I can go to meal rework, the first possible destination. And here on the rule, click on the rule. You see here we have probability. And you remember from the file that 12% of the parts go to the need meal rework. So the part can go to meal rework with probability of 0.12. So write it as a number between 0 and 1, not percentage. Okay, with probability of 12%. Fine. Another possible destination is that casting may end up at grinder rework with probability of 10%. Another possible destination was that casting may go to scrap parts. And that would happen with probability of 5%. And lastly, casting can go to finished part store. If we pass the inspection, we just directly go to finished part store, no problem. And that happened with probability of 73.73. Okay. So these are all possible destinations that we can have after performing the inspection operation. So as you can see, one line in the processes, but then on the destination side, we can have multiple destinations, and we specify the probability associated with each one of them. You have to make sure here the sum of the probabilities add up to 1, otherwise you get error when you run the model. Also, you want to make sure all of these possible destinations are just part of one block. We talked about that in previous session. So I don't want a separate block number for these routes. So all of them are just part of one block, okay? So we want to do that. Now,
excuse me, Professor.
Yeah.
What's the on the mill rework for the rule? It says the 12%, and then what's the 1 that's after it?
Sure, that's always the number that's even when we wanted to pick the rules for allocation of to parallel locations. Remember when we pick first available, it always says first 1 or turn 1. I always put the 1, just this is the first row or first part of this block that we go to. That's just automatic number that the rule window puts. Okay, now let's go back to the next line. My entity, which is casting. So let's assume the casting has ended up at meal rework. Where do we go from there?
To the mill.
We go to the meal machine to go over the rework. Do I need to tell the simulation where do I go after the meal operation?
No.
No, because?
Because it's already like set in the code, so it'll be just repetitive.
Exactly. Oh, the simulation already knows that if you get to mill machine, then where you have to go from there. So this is under the assumption that I assume that when parts go back for mill rework, then they go through the rest of the process like before, as if it's the first time that they are going through the process. So that's the assumption that I have here. So when I send them to rework to the mill machine, then I don't need to worry about the rest. I assume they go through the rest of the process. However, if that's not the case, if they go for the rework to the mill, but then they go through a different process afterward, then yeah, you have to capture that. But here I assume that no, after the mill rework or after the grinder rework, they go through the rest of the process like the past, so we're good. Now, let's assume the part ends up at grinder rework. Where do we go from there? To grinder. And next, let's assume the part ended up at scrap part pallet. Where do we go from there? We just exit the system. We can't do anything. I can't just leave the part sitting at the, yeah, in the real world, yeah, they sit in the scrap pallet, but in the simulation world, I can't leave a part at the location. Either I have to circulate the part in the model forever, or I have to send the part out of the system at some point. So after scrap pallet, they exit the system. And as last route, let's assume the part passed the inspection and ended up at finished parts store. And from there, they again go to exit. Now, I want you guys, okay, so first tell me this. Remember we were calculating work in process in previous model, and we started to increase work in process at receiving doc every time a new entity comes to the system. Now, tell me that where should I decrease work in process? I'm calculating working. Go ahead.
At the scrap and then finished part store.
Okay, I definitely decrease it once at the scrap because that's where parts leave the system. So they are out. As a scrap, that's fine, but they are out. That's where the number of items in the system, in the facility decreases. And also, like before, I have to also decrease it at finished part store because from there they leave the system. And just one more thing, guys, there is an inspection time. Let me give that to you. Okay, inspection time has triangular distribution, minimum 6, mode 8, and max 12. That's the inspection time. Okay. So we have processing time at the mill, grinder, and inspection. Now, also we had a product quantity. Remember the total quantity of the product that has been that has finished and have left the system. Do not define any variable other than the ones we already have talked about: the work in process and total quantity. So I'm putting that back as well. So the total quantity, remember, is the variable that counts number of parts that have been done processing and that have left the system. Now, I want you guys to calculate 3 things for me. I want you guys to calculate variables and count number of parts that need to go through the mill rework. I want you to calculate number of parts that need to go through the grinder rework. And I want you to calculate number of parts that have been scrapped, okay? When we run the simulation model, simulation does not generate these reports for us. Simulation doesn't tell me, oh, this number of parts need rework, or this number of parts need, this number of parts are scrapped. So I want you guys to define 3 variables. One, to calculate number of parts that need mill rework. Second one, to calculate the number of parts that need grinder rework. And then the last one, to calculate number of parts that have been scrapped. Okay, so please do that. 3 variables to do this calculation. find out where in the model you have to increase or decrease them. And I'm going to call your names and see how you guys are doing, okay? To calculate the number of parts that need mill rework and number of parts that need grinder rework and number of parts that are scrap, I define 3 new variables. I call them mill rework, grinder rework, and scrap, right? You can define these parts by going to the variables and define these 3 new variables, okay? You can name them anything that you want as long as you know what they represent. And then in the processing, if I want to calculate how many parts have failed the inspection due to mill rework and need to go to get mill rework, I can increase the variable right here at mill rework, which basically says when the part is mill rework, is in mill rework, then increase. Let me write it here. So in the operation window so that I don't need to retype. Increase mill rework. Okay, so that counts number of parts that have failed the inspection and have come to mill rework. And those are the parts that need to go through the milling operation again. For the grinder, that is increase grinder rework. When the part go to grinder rework, that means they have failed the inspection due to grinder operation and they need to go back to the grinder for the rework. And then also for the scrap part, when a part fails the inspection and is scrapped, I can also increase the variable that counts number of scrap parts right in the scrap parts pallet or location. That way, when a parts get to scrap pallet, then I'm going to increase this variable to count how many parts have been increased. Okay, one more thing. Remember in previous model, we had 1 minute move time between all the locations. So between all possible locations, we had 1 minute move time, okay? And that's the case after inspection as well. After the part is done with inspection, and if the part needs to go back to the mill for the rework, there is still 1 minute move time. If the part needs to go back to the grinder for rework, there is still 1 minute move time. And if the part is scrap and needs to get to the scrap pallet, there is still 1 minute move time for that, okay? However, so the question is here where do we put those move times? So in previous model, we had a 1 minute move time for going from receiving dock to mill. We are going to leave it as is. Here, the first line, we are going to leave the move time as is. And then 1 minute move time from mill to grinder, we are going to leave it as is. And 1 minute move time from going from grinder to inspection, we are going to leave it as is. And then after the part is done at inspection, then the part needs to go back to this other location for the rework and for the grinder and so forth. So I want you guys to pay attention to this. In the real world, with the high chance, or at least in the system that I'm modeling, it's not that there is a separate location for mill rework when I'm going to put the parts in there and then there's a lot of distance between this mill rework area and the mill machine. So the mill rework area is somewhere close to the machine. Grinder rework area is somewhere close to the machine. So as long as I do that 1 minute travel to put the part in the mill rework area, and then the person at the mill machine just picks up the part and perform the operation. Or as long as I do that 1 minute travel to put the part at the grinder rework area, and then the person at the grinder just picks up the part and start working on it. So what I'm trying to say is that it's not that we have to say, okay, there's 1 minute going from inspection to mill rework area and then 1 minute from mill rework area to the mill machine. That's not the case. At least in this model, it's not the case. So yes, for the sake of simulation, I put 3 different locations for the sake of simulation for the rework areas. However, in the model, if I want to capture the move time, I need to put the move time either going from either going from inspection to rework or going from rework to mill. So if I capture that 1 minute in one of these movements, then I'm good. I have taken care of the 1 minute move time for performing the mill rework, or 1 minute move time for performing the grinder rework. Okay, so let's put the 1 minute for going from inspection to the rework area. And we assume the rework areas are just close to the machines. So here, in the line when we go through the inspection. And after we go to the rework area, here I said move for 1 minute. A minute is not necessary. I just put it just so it reads well. And let's repeat that for move for 1 minute for going to the grinder rework, move for 1 minute for going through the scrap pallet, and move for 1 minute for going through the finished parts store. Okay, so that takes care of the movement of these parts that need the rework. And I'm not going to repeat that for going through the mill rework or grinder rework. With that, we are going to run the simulation for 100 hours. Okay, so no or yes. And if you guys go to, if you want to see the summary of your variables, where do you go? And here, okay, as you can see for mill rework, we have mill rework, grinder rework, and scrap parts. Now, what column is the most informative one when I want to report number of parts that need mill rework?
The maximum value?
Maximum value, because it's a variable that's going to increase by 1 every time a part needs mill rework. And so the maximum value shows the maximum number of items that need mill rework in that during the simulation time. And the same for grinder rework and the same for a scrap part. These are the variables that in the model, as you saw, we increase them every time a part needs mill rework or grinder rework or needs to go to the scrap pallet. So the maximum value shows the basically the information that we need. Does it make sense for me to report their average?
No.
No. For these items, average does not mean anything, absolutely nothing. Okay. For we also have work in process and total quantity from before. Okay, so we have those. Make sure to save, guys, what you have done so far so you don't lose anything. So here, as you can see, I have total exit as 398. In previous model, the number of parts, the total quantity variable that we defined, remember in previous model, we defined a total quantity variable that counted number of parts that finish processing and leave the system. And in previous model, that variable was equal, when we look at the values, that variable was equal to the total exit in the system, because total exit also shows number of parts that finish and leave the system, right? However, here, look at the variable total quantity 398, and then let's look at the variable, let's look at the variable total exit 398. And now if we go and look at the variable total quantity, it's 372. What is the difference between the two? So remember, the total quantity is a variable that we increase every time a part leaves the system. Why there is a difference between total quantity variable that captures number of parts that leave the system and the total exit that we see here, 398? Why do we see the difference?
Is it because of the scrap?
Because some of the parts get scrapped. Here, the total exit shows total exit, no matter if it's a good part or a scrap part. However, here, the variable total quantity that we define, we increase it at finished parts store. That's where we have good parts leaving the system. And then we have another variable that counts number of parts that leave the system as a scrap. And that counts total number of scrap parts. So that's why we see them in two sections. And that's why the sum of 372 and 26 is that number that we see here, 398, which is the total exit from the system, no matter if they left as a good part or as a scrap part. Okay, so pay attention to that.